In this video, we're going to be looking at Kinetics Part II, and in this part, we're going to be studying the orders of reaction and looking into integrated rate laws. So, in the previous video, what we looked at was discussing concentrations and rates, what a rate of reaction was, and the last thing we covered was how to write a rate law. And that's kind of where we're going to pick up here. So remember, rate law is where you take the rate is equal to K times the concentration of A to the M power times concentration of B to the N power. Now remember that M and N are the orders of reaction, and M and N are determined from experimental data, which is what we're going to be looking at in this video. Also remember that the overall order of reaction is determined by adding M plus N. So it's just a sum of M and N. Now that assumes if you have two reactants or however many reactants, but in this case it's just adding your exponents together. So this is an example of a data set that was collected for the reaction between ammonium and nitrite. And what we're looking at here are the number of experiments. In fact, there's 8 experiments. So what I want you to see in the first experiment here is that we have 0.01 molar NH4 plus, 0.2 molar NO2 minus, and the rate was observed to be 5.4 times 10 to the minus 7. If you know, the units are molar per second for the rate. Now, when you go to experiment 2, what you're going to see is that the concentration of the ammonium goes from 0.01 to 0.02, and then the concentration of the NO2 minus stays the same at 0.2. Now, what happens to the rate with that change in the concentration of NH4 plus 1? It goes from 5.4 to 10.8 times 10 to the minus 7. What we see here is that in these 2 experiments, the rate does double. Now the concentration doubles as well. So as you see from the NH4, it doubles. Now this doesn't matter because it stays the same. But what we're most interested in is the fact that the rate doubled as the concentration doubles. So what exactly does that mean? All right, we use this information in understanding how the concentration and the rate changes into determining your exponents M and N. This is how we're able to go about figuring out the orders of reaction. So we would figure out NH4 plus 1 using experiment 1, 2, because it changes in those 2 experiments, but then you hold the NO2 minus constant. You don't want to be trying to determine M and then having a varying concentration for the other. So that's why we use experiment 1 and 2. So as the concentration doubles, the rate doubles. That represents a proportionality. Then you have a first order reaction with respect to NH4 plus 1. And so we have to pay attention to how the concentration changes and then how the rate changes in relation to that change in concentration. So if we look at the NO2 minus, we would not use experiments 1 through 4 because the concentrations remain the same. But once we get to experiment 5 and 6, we see that the concentration changes for NO2 minus, but it stays the same for the NH4 ion. Now, if you look at the rate, so the concentration for NO2 minus doubles from 0.02 to 0.04. The rate also doubles. So that means that the NO2 minus is first order and how it's set up in the rate law. So as we write the rate law, rate is equal to K times concentration of NH4 plus 1 to the M power times concentration of NO2 minus to the N power. We see that M is 1 and N is 1. And that's based off of what happens to the rate as the concentration changes. So I'm going to go into a different document here, and we're going to look at a table, same table, and I'm going to show you, mathematically how we can determine the overall orders of reactions. So this is the same data chart that we just looked at, but if you notice here, you'll see that we have the rate of 2 divided by rate of 1, and then we have rate of 6 divided by rate of 5, and that's based off of the rate laws and looking at the difference in how they change concentration and the rate. So if we look at the way it's set up for this, the first part, which is NH4 plus 1, we see that we have rate of 2 divided by rate of 1, but we set up the rate law, and what we do is we add in the information from that particular experiment, in this case experiment 2, into the rate law. Now we also take consideration the next one, where we have the rate 1, and the rate 1 is using the information from experiment 1, and what we observe there is that now we have an algebraic equation we can solve for. So k's are going to go away. The 0.2n is going to go away because they're the same. They're just going to cancel out. And that leaves you with the 0.02 divided by 0.01, which gives you 2 to the n power. Then divide out the rate, and that gives you 2. So 2 is equal to 2 to the n power. Well, what exponent fits in there will give you 2 to what power gives you what? 2 to the first power gives you this equal to 2. So m is equal to 1 here. So it's first order, and that's what we were talking about in that first slide of the PowerPoint there with that table. And we look at the next set for solving for n. We have rate of 6 over rate of 5 because we were using those two experiments. Now you say, well, why wouldn't I put rate 5 over rate 6? Well, you can put it either way. Remember, it's a ratio. So in this case, we can either use it to get a whole number or we can get a fraction. I like working with whole numbers better, so I always put the bigger number on top, so that way I can get that whole number. So going through the math here, same concept as what we looked at in the first part here. We set it up, we find that k's cancel out again, and then 0.2 divided by 0.2 is going to cancel out, and that leaves you the 0.04 divided by 0.02, which gives you 2 to the n power, and then 21.6 divided by 10.8 is equal to 2. Again, 2 to the n power equals 2. What is n going to be? N is going to be equal to 1 in this case. So the orders of reactions, this is how you go about solving for it. So when we're talking about work, this is showing your work in relation to the problem that you're working on. Now, another thing we can do is we can solve for the rate constant, and the way we go about doing that is taking the experiment 1. I always use experiment 1. Experiment 1 is just the easiest one to work with. It's the first one you come in contact with. You can use it any of the experiments. It'll give you the same type, pretty much the same answer. So you separate it. You have your different parts. The rate is equal to k. What you want to do is get k by itself. So you divide out these two on the right hand side to the left hand side. You can see that I've done that here. And you got to make sure that you factor in the exponents again. All right, those exponents are still there. They were determined above. So when you get down to the bottom and you solve for this, what's going to happen, the units are going to cancel out and you're going to be left with specific units for k. So molar divided by molar cancels out, and that leaves you with reciprocal units of seconds here. And then if you notice that there's still 1 molar underneath, and this to the first power. So that's how we're able to obtain the molar to the -1 times seconds to the -1. And then just doing the simple calculation, you should end up with this answer here. Now, continuing on the units of k, you need to be careful in making sure that you know what order of reaction is. And in fact, the order of reaction is what determines the units for k. So this is a good example of where the rate is equal to k to the 8 to the first power is first order. Now the unit for A is molar, so we divide out the molar to the other side. Since it's to the first power, you only have one. The molars cancel out, so you end up with reciprocal seconds for K for a first order reaction. For a second order, well, the exponent is 2. Now keep in mind that we see an example here in that the orders of reaction were 1 and 1. The overall order of this reaction would have been 2. So this particular example falls underneath this example. It's just shown in a different manner. So we have molar squared divided out here. 1 molar goes away, and you're left over with molar minus 1 times seconds to the minus 1. And so the units are important. Just remember that the units of K are dependent on the overall order of the reaction. So we're going to look at another problem. So I've already worked this problem out, and I want you, let me get this blown up here. So this is an example where you have HgCl2 reacting with C2O4 2 minus, and what we observe here is we have HgCl2 in data, and then we have the oxalate data provided for us, and then we have the rates. So in the first part A, which says what is the order of reaction with respect to HgCl2, so I used experiments 2 and 3 because I want to make sure that oxalate stays constant, whereas the HgCl2 changes. So I go through the same process as that I talked about in the previous document, where you have to set up the rates. I set the bigger over smaller, and I solve for the order of reaction, which in this case is M. And so M is found to be first order. Now looking at part B, I'm going to use experiment 3 and 4 because I see that HCl2 remains constant, and then this changes. Now the little difference here, the difference is now, if you look at this, this is no longer a double thing. It's not like what we've been seeing in first order. So going through the math, what we observe is that this is actually 4 times is equal to 2n. So n is going to be second order. And that's a good indicator that you're dealing with a second order because they're not proportional to each other. Over here, you see that 2 is equal to 2m, but here it's 4 is equal to n. So they're no longer proportional. That as the concentration doubled, the rate quadruples. So n is equal to 2. So the overall rate law for this reaction is found to be rate is equal to K times HgCl2 to the first power times C2O4 2 minus to the second power. So the overall order of this reaction would be 1 plus 2 equals 3. So this is a third order reaction in relation to the 2 reactants above. And that's based off of the order of reactants that we've calculated here. So this problem does continue on to the next slide. So we will move on in just a second. So we looked at 2 different examples here. Now in the next section, we're going to be looking at integrated rate laws and what it means to be an integrated rate law and why we do this. So I'm going to kind of go through the slides here, and I'm going to switch back to another document. So integrated rate laws is basically using calculus to integrate over 2 different parts. In this case, we see that we have natural log of A is equal to minus KT. Keep in mind that the time changes and the concentration changes. You cannot integrate over 2 different things at the same time, so we have to separate them using the rate law that we observed from the experiment. So going through some manipulation, we get to the form. Now what I want you guys to make sure you pay attention to is this form here. Alright, so I'm going to circle this because this is what we're going to be using. So when we talk about rate laws and the integrated rate laws, remember earlier we talked about when you graph something. So if we graphed concentration versus time, and from that graph you got a curve, we talked about the fact that you can't figure out the slope very easily because it's curved. What we do with integrated rate laws is we graph it, and then this graph of an integrated rate law for a first order reaction is going to give you a straight line. So what we would see is, the graph would be observed like this initially. So, but if we graphed the natural log of A versus time, what we would see is a straight line. We can figure out the slope of a straight line a whole lot easier than the slope of a curved line, or in this case, a curve. So this is what we want. So this is the whole point of integrating the rate law, is to get a straight line. And that's what a lot of the calculus that we use for is, so that way graphically we get a form where it's easier to use and to work with. So if a reaction is first order, plot of natural log of A versus time will yield a straight line. And the slope of this line will be equal to negative k, because if you notice, the slope y equals mx plus b. So here you're going to get a negative slope, and that negative slope is representing the rate constant. So ideally, what you get from the graph, you can determine, first of all, whether it's first or second order, and second, you can determine the rate constant from the slope of that best fit line. So here we got a set of data that was collected. We see that we graph toward pressure, concentration. We graph pressure versus time. We get this exponential decay. All right, so that's important. It shows us that as the time progresses, the rate changes. It slows down. But when we graph it using the natural log form, so the first order, when we graph the natural log of the pressure, pressure is the same as concentration in this case, so it's not going to change it, even though they're different units. So natural log pressure versus time gives you a straight line. What does that tell me? That tells me that the reaction itself was first order, because it gives you this straight line. And again, what do you get from the slope of this best fit line? You can determine the rate constant for that process. Now, second order, what we see here is a little different than first order because of the way we go about integrating it. But the form that you get that's important here is this form here. You notice I scribbled out some stuff there because there was an error in that part of the slide. So ignore that. But what you observe here is that you have 1 over the concentration of A versus time. So you'd have a graph of 1 over concentration of A versus time. And here you would have a graph that looks like this. It would be a straight line. Again, what's the point? The point is to observe that for a second order process, you get this straight line. That's the whole point of integrating the rate law. So look at another example where we have NO2 breaking down to NO plus 1/2 O2. This is the basic information that you get initially with time and concentration. So as we graph that, we get a graph that would be a curve. Now, I don't have that graph shown on here, but what I do have is the graph of natural log of concentration versus time. Now remember, the natural log is representing first order, and what you see here is a curve, and that curve is not something that you want to see. So we know that first order is not the order of this particular reaction because it's not a straight line. So when we go about graphing the 1 over concentration of NO2 versus time, now we get a straight line. We see that straight line here. And that's important because what does that tell me? That tells me that this process, this reaction, is second order. Now, also from the slope, you get K. So K is determined from the slope, same as what we saw in the first order. Now, before I get into the half-life, so I'm going to go back to the previous document we're looking at. So I want you to understand that there is zero order, and I want to make sure that this is something that is not ignored. So zero order is basically a graph of concentration versus time. Now, we did talk about before where if you graph concentration versus time, usually you're going to get a curve. That's typically what you see, but not the case if you have a zero order process. A zero order process is going to give you a straight line, and that's determined from the graph. Now, there are different half-lives. So let's talk about half-life second. So half-life is the amount of time it takes for half the reactants to decrease in their concentration. If you were to flip a coin 100 times, how many times would you hit heads? Should be 50 times. Now, if you flip it 50 times, how many more times should it get heads? You should get 25 times. And what you see is this exponential decay. And that's when we talk about half-lives, is how much time it takes for half the concentration to go down. So if you start off with 1 molar, half of that is half. So it takes how much time it goes down by half a molar. And then half of the half is 0.25 molar. So now, I don't want you to be confused with that. It sounds kind of funky, but either way, each of the orders of reaction have their own unique half-lives. So if you find out that you're working with a zero order reaction and you need to figure out the half-life, well, this is the equation that you would use. So write this down on a flashcard so that way you have it. So this is relevant to zero order reaction. T1 half is equal to the initial concentration of A. This little zero means initial concentration. Let me blow this up for you. So again, this zero represents initial divided by 2K. Well, if you have the graph, guess what you figure out from the graph? You can get the initial concentration, you can get the rate constant from the slope of the graph, and you plug it in, you solve for the half-life for that reaction. Now, for first order, the half-life is 0.693 divided by K. A little easier to work with because all you have to do here is figure out the rate constant for that reaction so you can figure out the half-life. If you knew the half-life, you could figure out the rate constant. So write that equation down. For second order half-life, you end up with this equation here. T1 half is equal to 1 divided by K divided by the initial concentration of A. So again, K comes from the slope, and then A is coming from the data chart that you're given. Now, a good example of what you might use for this is found here on this slide. So I'm going to blow this up here. What I want you to do is I want you to take a minute to go through, and I want you to sort of draw use the data that's in the chart there and draw these graphs. I'll come back in just a minute and show you the final result, what you should get. Okay, so we're back here and I have the graphs drawn. Ignore the fact that my line on the left is a little wobbly. I needed a ruler, but I didn't have one. So, but what we do see is that if you look at graph 1 compared to graph 2, the natural log of A versus the 1 over concentration. So this would be the graph you want to use. And what that tells me here is that the natural log of A represents the first order. So this process of the radioactive decay of iodine is first order. So we would not use this because it's a curve. You can see it's not a straight line. So in the next video, in part 3, we're going to begin talking about the collision model and temperature versus rate. So tune back in for that video. Thanks for watching.